Hey everybody, today we're going to start getting into chapter 7. We're going to start looking at ionic bonding. So this first video, I just kind of want to summarize a little bit of what ionic bonding is. This is again meant to be supplemental with your book as well and the discussions you have in class. So let's get into it really quick. First of all, thankfully, we do have elements and atoms that will bond together. But why? Why do they bond? And why do some things bond and other things don't bond so well? Hopefully you've taken a pretty in-depth look at the periodic table and you've noticed that there is one specific group or family on the periodic table that doesn't bond very well. We call them the noble gases. We used to call them inert gases due to the fact that they don't react. Now, can we make them react? Yes, there are circumstances we can make those gases react, but they certainly won't do it in nature. So what makes them unique versus every other element on the periodic table? Well, if you think about it, there is something unique about all of those particular elements. They all have a full valence shell. And what we have found is that due to that full valence shell, they really have no inclination to bond. So when we're saying, why do other things bond? It's because they're looking to get a full valence shell. And there's a lot of different ways we can get a full valence shell. We can have one thing take electrons from something else to get a full valence shell. We can have two different kind of elements share electrons to complete a valence shell. We can have two of the same kind of elements share electrons to complete a valence shell. So there's a lot of different things that happen. Ionic bonding discusses one kind of way that we have. So what is ionic bonding? Ionic bonding in general is a bond between a metal and a non-metal. If you remember from your periodic table, the left side of the periodic table is metals, there's more metals, and the right side is non-metals. And when we have this happen, we see such a significant difference in the numbers of valence electrons that it plays into kind of the energy that is required for bonding to take place, okay? Another thing that we could say, although you won't be tested on it, is that when we have an electronegative difference, between the two elements that is greater than 1.7, we'll have an ionic bond. Now the reality is in class, we're going to talk about ionic bonding versus something that is a polar covalent bond, okay, which is where they're sharing but unequally. The reality is it's all kind of along this spectrum of electronegative difference. And so they can kind of bleed together a little bit on each end of both those spectrums, okay? So how does that work? What ends up happening? Well, we can look at the periodic table and determine when looking at the group number or the family number, how many valence electrons a particular element has. This is true in every group except for that main body in the middle called the transition elements. Those transition elements, you will not necessarily know exactly how many valence electrons they have. And it can change unless we give it to you in the name, which we're going to get into later. So let's talk about something pretty straight ahead. Probably the most common ionic compound that I can think of is sodium chloride. Sodium chloride is table salt. Sodium chloride is a metal and a non-metal, okay? So how do these two things come together? Well, what happens with ionic bonding is sodium is sitting here, and I want to give you a second to look up on your periodic table where sodium is and where chlorine is, and identify how many valence electrons each of those two things has. Hopefully you found that sodium is in group 1 or group 1A, so it has one valence electron. I'm going to do some dot structures while doing this. And chlorine has 7 valence electrons. And again, I just put some as little X's and some as dots just to differentiate for myself. What we should also know is when we look at that periodic table, as we move from left to right across the period, electronegativity increases. And as we move from the bottom to the top, it increases. So if we look, we'd also see this great electronegative difference. But for us, we're just looking at and saying, we have a metal and a non-metal. So what happens? The non-metal always takes from the metal. And you go, okay, I see how that works for chlorine. Chlorine now has 8 valence electrons. But how about sodium? Sodium only has one valence electron. Or excuse me, sodium now has no valence electrons. So isn't it unhappy? And the answer is no. Actually, it is happy. And the reason is because once it has lost that valence electron, it drops down to the next energy level where you have a full valence shell. So everybody's happy. So these come together in a 1-to-1 ratio. Everything's good. Everybody's happy. Sodium is a plus. Chlorine is a minus. This gained one electron. So it's a charge of -1, or we can just put minus. And this lost an electron, so now it's a charge of +1. It has one more proton than electron. But what would happen if we had something different, like magnesium chloride? I'm going to give you a second here again. What if we have magnesium and chlorine? And these two things are going to bond together. What's going to happen there? Well, look up again, first on your periodic table, how many valence electrons does each have? We just talked about chlorine. It has 7. Magnesium has 2. So again, if you're following along with me, this is in group 2A or group 2. This is in group 17 or 7. 7 and 2 for valence electrons. We know that it's a nonmetal and a metal. We know that it's always the nonmetal who takes. Nonmetals are the bullies. They'll come in and take those electrons. And magnesium's going to lose. But what happens here? Chlorine takes one valence electron. Chlorine says, I'm happy. I got my full valence shell. Magnesium's going, whoa, slow your roll. I still got a valence electron. I'm not done yet. Chlorine says, what do you want me to do? Magnesium says, bring a friend. So chlorine brings a friend with 7 valence electrons. And it takes a second one. And so let's look and think about the relative charges now of these ions. Each anion, or negative ion, has now gained 1. So this has a charge of -1. This has a charge of -1. Magnesium has lost 2, so its charge now will be 2 plus, or +2, however you want to write it is fine. And we can write out the formula then as MgCl2. And that's always going to be the formula for magnesium chloride. Every single time you see magnesium chloride, it's going to be MgCl2. Always the exact same way. Let's do one more example. And instead, how about magnesium nitride? Magnesium and nitrogen. If these two were to bond together, what would that end up looking like? Well, again, magnesium has 2 valence electrons. We learned that in the last one. And if we look up nitrogen, how many does nitrogen have? 1, 2, 3, 4. It has 5. So again, magnesium is my metal. It has fewer valence electrons, in case you forget. The one with more valence electrons is going to be doing the taking, nitrogen. And it says, give me a valence electron. Give me a valence electron. Magnesium is now happy. 2 plus or +2. Nitrogen is like, whoa, I only got 7. I need an extra one. So now, just like magnesium did with chlorine, nitrogen looks at magnesium and says, bring a friend. So it brings a friend. Boop. Nitrogen takes that valence electron. Nitrogen has now gained 3. Whoa, nitrogen's happy. But now what about this guy? He says, not done. Bring a friend. Write it more accurately. With that one left, he goes, I'll put it there. And this magnesium says, I'm happy. I'm happy. But this nitrogen now is like, dude, I only got 6. I need 8. So what does he say to magnesium? Bring a friend. One, 2, +2. This gained 3, -3. You can always check your math to see if it worked. Plus 2 plus 2 plus 2 is plus 6, minus 3, 0. You'll always end up with a sum of 0 if you look at these relative charges on both your anion and cation and add them up. And then we write the formula. There are 3 magnesiums, so we use this subscript. Oop, not S. 3. And nitrogen, 2. Okay? Now, this is great if we're drawing dot structures, but not always the most practical, and certainly as you get more into it, you're going to want to be able to and probably be able to write these a little bit shorter and easier. Here's a quick way to look at that and a way to do that, to write those formulas. Okay? Let's just look at the back. I'm going to pick out 2 random. I'm going to say calcium fluoride. Okay? So calcium and fluorine. Okay? Calcium is in group 2A or group 2. So it's going to have 2 valence electrons, consequently that it wants to get rid of to go back that energy level. Fluorine has 7, meaning it needs to just get 1. So it has a charge of minus 1. Easy way to write this out, crisscross applesauce. Ca, if your subscript is 1, you don't have to write it. F2. There you go. If you can simplify the ratio, anytime you do this, you do it for ionic compounds. And that's the basics of getting into ionic compounds. We'll see you next time.